Hey everybody, welcome back to Comp 1113, Unit 2, Signed Integers. This will be video number 1 of Unit 2. In this video, we're going to start talking about how to deal with negative numbers or integers. There are various formats and coding systems to storing these integers, so we're going to discuss 3 of them today. One is sign magnitude. The next is ones complement, and then finally we'll get to the greatest one of all, two's complement. Here's a number, 1101. What is it? If that's a binary number, that's the number 13, 8 plus 4 plus 1. If that's a decimal number, I guess it's 1101. If it's an octal number, it's 577. If it's a hex number, it's 4,353. Go ahead and do the conversions yourself to verify these values. But maybe it's other things as well. Because a computer is always using zeros and ones, we have to have many different ways of interpreting various bit strings. We said that 8 bits was a byte. This is a 4-bit number, so it's a nibble. This number, if it's declared to be an unsigned integer on 4 bits, is the number 13. If it's a signed integer, then this is actually the number -3. If this is a signed magnitude form anyway. And if this were an ASCII character, this would be a carriage return. So every string of zeros and ones will have different ways of being interpreted. We're going to discuss negative numbers, or basically integers. We have to discuss positives at the same time. One way to code or make room for negative numbers is to sort of split up our bit strings. What I did here was I listed all the possible permutations of 3 bits. 000, 001, 010. In fact, I listed those permutations in order. Now that we know how to convert to and from binary, the number 0 in base 10 is 000 in 3-bit binary. And the number 1 is 001, and 2 is 010. So I didn't just write these down completely, randomly, but it does list all the possibilities for 3 bits. We're doing the 3-bit example just because it fits nicely on the lecture slides. In real life, we would obviously use more bits when we are representing integers, 16-bit, 32-bit, 64-bit, etc. So in these small examples, we will have a fairly limited range of numbers to work with. On 3 bits, we can only represent the numbers 0 through 7. I want to assign some of these to be our negatives. So we'll just come up with a rule. One rule is to say anything that starts with a 0 will be a positive number, and then anything that starts with a 1 will be a negative number. This is called the sign magnitude way of representing integers. So what we do is we have the first bit indicate the sign, and then the rest of it is the size of the number. So 100 is going to be negative, and then the rest of it is the size of the number, so 0. There it is. And then the next value down is -1, -2, and -3. So now we have a way that we split these codes up so that we have both positives and negatives, and we just need to know the rules. If it starts with a 1, it's a negative number. If it starts with a 0, it's the positive value, and the other 2 bits tell us the size of it. It has a great name. It's a sign with a magnitude, where 0 means positive and 1 means negative. Now, this this is a really nice system because it's super simple, but it does have its downfalls. Sadly, we don't use sign magnitude. When you declare something as an integer, when you're programming, it does not use sign magnitude to store the values. We do use sign magnitude when we're talking about floating point numbers, so I want to make sure that we're aware of sign magnitude right from the get-go, but technically we don't use it that much. But it is a simple code. The reason that we don't use it that much is there are problems. One, we have two zeros. We have positive 0 and negative 0. Another problem, and probably the biggest problem, is that math doesn't work. When we go to add two of these values together, we don't get the right code. So if I add the code for 1 to the code to negative 1, we don't end up getting necessarily the number 0 as expected. For some of them it may work, but many of them it doesn't work. So math gets hard in sign magnitude. We can't simply just add the binary strings together. So we're going to try to improve on this to make math easier, even if it means that we'll add some complexity to the conversion to and from base 10. Here's an example. If I try to add the number 2 and the number negative 1, if I take 0, 1, 0 and I add it to 1, 0, 1, 0, 1, 0, and I add it to 1, 0, 1, these are, I'm going to make a subscript SM for sign magnitude. If we add those two strings together, we get 1, 1, 1. Well, the first number was the number 2, and the next number was the number negative 1, so we're expecting our answer to be 1, but our answer is turning out to be negative 3. So, maybe we can put a sad face there. Math doesn't work, at least addition. I still will ask of you to be able to convert back and forth between sign magnitude and integers. Whenever we're talking about a sign magnitude number, we'll always have to talk about the number of bits we have. If this were the number that I have written here, if this were on 10 bits, I would have a few leading zeros. So you always have to know how many bits you're dealing with so you know where the sign bit is. So here's an 8-bit number, and I know it's a negative number because it starts with a 1. So the first bit is your sign, and the rest of it is its size. So we have 1, 2, 4, 8, 16. So this number ends up being negative 16 plus 8 plus 4 plus 1, which is negative 29. So it's like I said, it's pretty. The nice thing about sign magnitude is its convenience. It's super easy to do these conversions. I'm going to just erase that so we can watch the PowerPoint fill in. Although it doesn't show much work, negative 29. If we want to go the other way, suppose I have a number negative 42 and I want to convert it to its 8-bit sign magnitude. Basically, I have 8 bits. The first one is the sign, and because it's a negative number, I'm going to put a 1 there. And then I need to build the number 42. With the remaining bits. Now, if we try to do negative, 300, it's not going to fit on 3 bits. So we are limited by the number of bits we have in terms of what our max and min are. I guess we can go down to negative 127 here. But to make this number negative 42, I need to make a 42, so I don't need any 64s. I do need 32, and now I need 10 more. So 8 and 2. And then the rest of these will be zeros. So we were able to store negative 42 on 8 bits in sign magnitude. Be careful, I keep doing examples of the negative numbers. If I asked you for positive 42, you wouldn't have to do anything with the first bit, it would just be a 0. The positive 40, all the positive numbers are going to work like what you've been doing up until this point. You're just going to convert them to their binary strings. I'm going to wipe this off of here. And watch the PowerPoint fill it in. Hopefully it matches what we came up with. But we won't use sign magnitude that much, except we will discuss this whole idea of having a sign bit as we move into floating point. Primarily because of the addition problem that we mentioned. We can try to come up with another code. Instead of having our values have a sign and then a magnitude, what we could do is do this thing called ones complement. Basically, if you want a negative number, you figure out what the positive number is, and then you complement all the bits, and that means change them all. So for example, the number 1, positive 1, will be 0, 0, 1 on 3 bits. So to figure out negative 1, I'm just going to change them all. 1, 1, 0. I'll put a subscript 1c for ones complement. Now this is another very simple way of coding this. It's easy to do the transitions between them. If you know the positive value of the number you want, just change all the bits and that's the negative number you want. Filled in the chart here, you can watch like the number 0 is all zeros, negative 0 will then be all ones. So it's not too bad to do conversions, but this ones complement also has a problem. Its math doesn't work, and it does still have the problem of having a wasted spot of positive 0 and negative 0. One thing that is nice is that it does still follow the rules of sign magnitude, where you can tell the sign of the number simply by observing the first bit. But be careful here, in ones complement, the first bit isn't just the sign, it's also part of the number. So in ones complement, you don't look at the number as two distinct pieces. That's a common error I notice that students pick up from this. Yes, I can look at this string here and I can tell that's a negative, and I can look at this string and I can tell that's a positive. But to convert them, I still have to flip all of the bits, not just the leading bit. I'm going to ask you to be able to convert to and from ones complement as well, even though it has its problems, 2 zeros, and addition doesn't work again. When you try to add 2 plus negative 1, you do not get what you expect. In fact, in this case, we would end up with too many bits, which isn't always a problem when we're adding two integers like this. Sometimes it isn't a problem at all. We'll see that when we learn the next one. But if you add 0, 1, 0 in ones complement, to 1, 1, 0 in 1's complement, you get 0, then 0 carry the 1, and then 0 carry the 1. You see that you end up with 1, 0, 0, 0. If we ignore the carry out and just look at the 3 bits of the addition there, we still don't get the right number. We're expecting the answer to be positive 1. So we're hoping that the answer is 0, 0, 1, as you can see. So sad, another one doesn't work. And I'm going to make you know it anyway. This is a stepping stone to getting to a way to store integers that actually does work. So just be patient here. We're kind of going through the evolution of various coding schemes, and eventually we'll get to one that actually works. Before we do that, we'll do a quick conversion. I look at this 8-bit 1's complement number. Sometimes I write it with a subscript 1c. I can tell that it's a negative number right off the bat. So to figure out what number it is, I'm going to first write down a minus sign, and then I'm just going to flip all of those bits and figure out what this number is. So it goes, 1, 2, 4, 8, 16, 32, 64, 128. So we end up with negative 64 plus 32 plus 2. Looks like it's negative 98. So step 1 when you see these problems is figure out, is it a positive or negative number? If it's negative, flip all the bits and then figure out what number it is. If it's a positive number, don't do any flipping. Just figure out what number it is. It's like a trick question on the midterm. Question 1 is a negative number, question 2 is a negative number, question 3 is a negative number, and then I'll throw in a positive number, and you'll be in sort of this algorithm of here's how I do the negatives. You'll flip the bits when you shouldn't. You don't need to flip anything if you have a positive number. In the PowerPoint, it kind of flies in pretty fast. I showed a little extra work here. If we're going the other way, you have negative 42 again. Well, first I write down what 42 is on 8 bits. So as an unsigned, to make 42, I don't need any 128s, I don't need any 64s, I do need a 32, I don't need a 16, I need an 8, I don't need a 4, I need a 2, and I don't need a 1. 32 plus 10 more gets me to 42. This is just regular old binary. Now to get negative 42 in 1's complement, I simply flip all of those bits. So the procedure is nice, but sadly it doesn't work when we add. You'll get to do a bunch of these conversions in your next set of exercises, I'm sure. There's the number 42, and then I complemented all the values. So our final answer there is at 1's complement. Again, reiterating, 2 representations of 0 is not great, and adding not working is not great. So we will improve on it with the next one. The next signed integer you better start paying attention to, because this is the one we're actually going to use. It's called 2's complement. it's a lot like 1's complement, except we shift. We simply shift all of the values of 1's complement down, all the negative values, down 1 spot. What that does is it accomplishes getting rid of the 0. I'm just keep replaying this over and over because it took me a long time to get that slide to work in PowerPoint. Anyway, so we shift everything down, which makes room for 1 extra negative. So our range won't be as symmetric as before. We get an extra negative number. We'll call this spot -4. The same pattern applies to 4-bit, 5-bit, 6-bit. I'm just doing the 3-bit example because it fits nicely in the lecture, even though I can't imagine you ever having 3-bit integers for many things. The beauty of 2's complement is it fixed the 2 zeros problem, and believe it or not, it also fixes the addition problem. When we add the binary strings together, we actually get the result that we should, provided that we're still in the range. Like on 3 bits, the only thing we can have is -4 up to +3. So if I add 3 plus 2 and get 5, obviously that doesn't make sense because I can't store 5 on 3 bits. But as long as whatever I add together still fits in the domain of these values, then everything it works. It's amazing. And the conversion to and from 2's complement isn't bad at all. It's basically like your conversion to 1's complement, except you just have to shift everything by adding 1. So now we finally have something that's going to work called 2's complement. Another neat feature of the thing is that it continues to preserve that the negative numbers start with 1 and positive numbers start with 0. So we can quickly look at a binary string and we know if it's positive or negative. Another neat thing is the way that you do the conversion to and from 2's complement. It's neat that the algorithm for it is the same in both directions. So a little animation coming here. The relationship between +2 and -2. I flip the bits of 2, and then I add 1 to this string, and that gives me where -2 should be. And if I want to go backwards, if I have -2, I can just flip the bits and then add 1, and I know that its corresponding value is +2. So that's pretty neat that you don't even have to have subtraction. Usually when you undo addition, you say, well, I'll subtract 1 and then take the complement. But you can make it even simpler than that. It's just always flip all the bits, add 1, regardless of the direction. So it's nice to only need one algorithm, because you guys are starting to get a bunch of various algorithms that you have to keep track of. So this one is nice that it's the same in both directions. This one has no problems. It only has 1 0, and addition works. Suppose I want to add 2 and -3. I take the number 2 and I convert it to 2's complement. Since it's a positive number, it's just whatever its binary string is. In this case, we're doing 3 bits. So 2 is 0, 1, 0. I'm going to write a 2C for my subscript. Then I'm going to take the number -3. That's the number 1, 0, 1 in 2's complement. When I add them, I end up getting the answer 1, 1, 1 in 2's complement. And you'll see that that does equal -1. 1, 1, 1 is -1. So math works. This is actually how integers are stored. When you declare a variable as an int, it is stored in 2's complement. The number of bits may vary, but the method will be 2's complement. So once we learn this procedure, we're in really good shape. So 2's complement is a wonderful, wonderful way to represent integers. We'll do more examples of this as we get into our next video. So I think that's enough for this one, and I will see you all next time where we show more 2's complement addition and some overflow conditions, and then we'll introduce a few more ways to represent integers. Have a good one.